All right, welcome to the last subunit in this unit before your big first academic adventure. We are today going to focus on reaction rates, sometimes called reaction kinetics. In other words, how fast reactions take place. Sometimes they take place super fast, and sometimes they take place so slowly. And there are factors involved in why that happens. And we need to go through those factors and do some sweet calculating. Now, here's what I want you to do, though. Again, I always refer to if we were meeting because, of course, if we were, then the last time that we would have met, we did all that colligative property stuff. There was one, I like to just get a jump on reaction kinetics by ending colligative properties with starting reaction kinetics. So if you were to go back and get, and some of you might have noticed this, that on that last handout that had all the colligative property problems, there was a number 6 problem. I did problems 1, 2, 3, 4, and 5 on colligative properties. This is not a colligative property. It's a reaction kinetic property. And the reason I do that is because, well, there's a lot of reaction kinetic property problems I have to do, and I just wanted to get a jump on it. I didn't do that. So what I need you to do, okay, so I'm saying, bottom line, what are you saying? Bottom line is get this sheet. We need to go through this problem number 6 on the sheet from the previous material on colligative properties. I need to go through that. So here we go. So this video is just about introduction and going through that last problem on that last sheet. Okay, you also want to grab it of essential documents, this bad Larry here. Okay, it's got reaction kinetics and all the things and terms that I have to go through with this last subunit. Okay, diving in. If we have a reaction that takes place, let's say it's A plus B makes C. Okay, a couple of compounds come together, they synthesize, and they form this stuff. If I know that this is reacting at a rate of, now rate means per unit of time. That's what rate means. It's something over time. Like your speed is a rate. It's how many miles per hour you're traveling. It's a rate. So a rate refers to how fast something happens, and we always use in chemistry, and usually in physics as well, seconds per second. So let's say that this chemical is being used at a rate of 2 m per second. 2 molars per second. Okay, now remember, molar is a concentration. So this is being used at a rate, it's being used up at a rate of 2 moles per liter per second. Because remember, that's what molarity means, is moles per second, moles per liter. So this is being used up at a rate of 2 m per second, and this one's being used up at a rate of 4 m per second. Of course, in real chemistry, not that this isn't real chemistry, but it is. But of course, in real examples, it's never so nice and perfect like that. Usually not, but okay, well, we can introduce it here, so we're good. And it makes this chemical at a rate of 3 m per second. Again, I'm just making these numbers up just to prove a point. Let's say that this is the rate of the reaction. 2 of these get used up, 4 of those get used up per second, and we make 3 of these per second. All right, so what would happen over time is we would lose this. We would lose this because we're using it, and we would make this. So over time, we lose this. That's what the negative means. We lose this, and we gain this. Okay? Kind of makes sense, right? So this stuff goes down, this stuff goes down, and we're making some of this. And we'll find very soon in the next set of videos that reactions don't just go in one direction typically, okay? They usually go back. But I'll stick with the one direction here today. Okay, now where's the problem here? Okay, so this is very much what this problem here is referring to. So, okay, let me give you a real quick example and see if you can figure this one out. If the rate of this reaction increased, I mean things like temperature rising increases your rate of reaction. Maybe we dumped a whole bunch more of A and B in the solution, so we have more of it to react. Whatever the reason is. Let's say that this one increases in its reaction rate to 8. So it doubles the amount of it that's being used up per second. We've doubled it. So the reaction's speeding up. Make a prediction for me. Tell me how much of this must be getting used up now. 2, 4 makes 3. Now some of you might be saying, how does 2 plus 4 make 3? Well, no, it doesn't. It's talking about moles, and these compounds are going to have different weights and numbers of stuff, so it doesn't, I'm not saying that 2 and 4 make 6. I'm not saying that. But let's say we double the reaction rate of this compound from 4 to 8. What must happen to this one? It has to double. It has to. If this one's going to double, this one must be doubling in its rate that it's reacting. Oh, this one couldn't double. So this one must go to a 4. What about this over here? How much of this are we now producing per second? Well, if we doubled the consumption of these, meaning that we're doubling how much we're losing here, we must be doubling how much we're gaining here. This must be going up to a production rate of 6 molar per second. That's what's called reaction kinetics. Now, that's real simple reaction kinetics. And some of you might be going, that wasn't so simple. Okay, well, it's relatively simple at reaction kinetics, meaning that we can look at what are called the rates of the reactions. And rates, remember, mean per second. So how much of this stuff is being consumed? 4 moles per second, 4 moles per second, 2 moles per second, make 3 moles of this per second. And if I were to double this one, then this one must have doubled, otherwise I couldn't have doubled this one up. So that's got to double, and now we're doubling the amount being used up, we're doubling the amount being made. Okay, that's the idea behind reaction kinetics. Okay, well, that's not so bad. Let's actually do a problem. I just made up some letters here and some values. Let's go ahead and do a problem, and that's problem number 6 from the colligative properties sheet. So let's go ahead and do that, and it says we've got 4 nitrogen dioxides, and that's reacting with O2, and we're going to be making 2 dinitrogen pentoxides. All right, let's just make sure it's balanced. It should be balanced, but I wouldn't put on the sheet, but there's 4, 8, 10, 10. Okay, it's balanced. So now we have this reaction. Here's just a reaction. Now we're given some rates at which this stuff is reacting and being formed. Let's look at the equation sheet. And it says, suppose at the particular moment during the reaction, oxygen, molecular oxygen, is reacting at a rate of 0.024. So this is my molecular oxygen, and it's reacting at 0.024 molar per second. So 0.024 moles, if we had a liter of it per second, are being used up, used up. So I'm losing this oxygen at a rate of 0.024 molar per second. Okay, question A. At what rate is the dinitrogen pentoxide being formed? At what rate would this be formed? Well, I can't do that. I don't have another reaction rate. You didn't give me another reaction rate. Actually, we did. We know from the balanced reaction, the ratio of this and this, making this, is a 4 to 1 to 2 ratio. That's the rate that we're going to be using. In other words, for every one of this that gets used up, we need 4 of these, and we're going to make 2 of those. So if this is the amount of stuff here, we look at the ratio from the balanced equation to determine what the rates of the others must be. The first one was how much is being formed, and the second question is going to be at what rate is the NO2 being used up. So, okay, so this produces twice as much of this. So if this is being used up at a rate of 0.024, this must be being made, and made, we put a positive. We're losing this, that's why we have the negative, of double this, 0.048 molar per second. How did you get that? Because from the balanced reaction, it's a 1 to 2 ratio. So if this is being used up at 0.024, this must be being made at twice this one, or 0.048 molar per second. What about this one? It's a 4-to-1 ratio here. 4 to 1. So if 0.024 of this are being made, then 4 times that are being consumed. Then this one is being consumed at 4 times that rate. 4 times 0.024 is 0.096. So this is going to be used up at 0.096. You just have to make sure that your numbers are in proportion with the balanced reactions. The balanced reaction will tell you what the rate used and the rate made are going to be. And you just have to know one of the rates. So you have to know one rate. If you don't know one rate, you can't figure out the other ones. So we were given this one from the balanced reaction. This one's going to make twice as much of this one. And this one's going to be used up 4 times as fast as this one. So 4 times as fast. Okay? That is a relatively simple application of rate, how much something gets used and how much something gets made depending on the balanced reaction if we have one of those rates. Okay, that is that last problem done on that sheet. Now we get to go to our new problem sheet for today. And we got a bunch of problems to solve on there, and I cannot wait.